Hey guys, it's Charlie back again with another lecture in our machine learning lecture series. So, today I'll be giving a virtual lecture that was supposed to be given before our guest lectures, but unfortunately, as you all know, our time together was cut short by the COVID-19 crisis. So I'll be presenting this lecture to you virtually today. I'm going to try to do it in this Khan Academy-esque style where I'll be writing onto this virtual whiteboard. Let me know what you guys think of this, if it's any better than just like traditionally writing it on a piece of paper and taking a video, or if you guys like the style more, if you can understand the content maybe easier. And yeah, without any further ado, let's get started. So today we're going to be talking about meta-learning. Meta-learning, put simply, is the process of being able to learn how to learn, and doing this both quickly and efficiently. So these are the two major points that I want you guys to keep in mind as we progress through the rest of this lecture. And just for some more basic info, there are many different terminologies used in meta-learning, and we're going to be sticking with the ones defined by DeepMind researchers from Google DeepMind in their seminal paper in 2016. And basically what we're going to be talking about today is an optimization-based style of meta-learning. And what this means is that we're going to be focusing on being able to optimize an optimizer to be used to learn how to learn. One other thing to note is that in the past, right, with your traditional vanilla machine learning models, we've been able to very easily and very efficiently take in a large amount of training data and use this to solve one specific problem. But the goal of meta-learning isn't to only solve one thing. It's to be able to generalize over a wide array of tasks and basically create a learning algorithm that's able to follow a set of experiences and through this learn how to learn and be able to learn new tasks easier if they're similar to other tasks learned beforehand. So diving into some of the background behind meta-learning, like I said before, the general goal of these meta-learning systems is to be able to create and train some kind of learning algorithm that's able to function well to help neural net models learn over an entire class of problems. And this learning algorithm, it can be typically viewed as the optimization algorithm or an optimizer for training a neural network. And the ultimate goal of creating this optimizer, this learning algorithm, is to be able to make it function better than if we were to just handpick some generic optimizer like Atom, RMSProp, SGD. So with this optimizer we're going to be training, our goal is to have this optimizer function better and allow our models to learn more quickly and more efficiently. So now we're going to define two more terms. We're going to define something called a base learner and a meta learner. So our base learner, you can think of this as just a generic vanilla neural network, some kind of supervised learning neural network that's just able to take in a training set, so you have your features, your labels, and just output predictions. And the next thing we have to define is our meta learner. So our meta learner is, as the name implies, a higher level neural network that's able to sequentially train the base learner in a way that allows the base learner to use a optimization algorithm that's being trained and refined by the meta learner and use the metrics returned from the base learner that's using this optimizer to be able to improve upon itself and keep on refining and building a better optimization algorithm. So the key takeaway here is that the meta learner is the one that's training the optimization algorithm. And this optimizer is being used in the base learner neural network. So in whatever the base learner is doing, the base learner is not going to be using some generic defined by humans optimizer. It's going to be using this optimizer that's given by the meta learner and that's being trained by the meta learner. So the next thing that we're going to have to define is something called a family of tasks. What do we mean when we talk about a family of tasks? Well, we basically need to hit on three key points. The first being, all of these tasks, all of these problems that you're aiming to solve, they have to be similar in structure, and they have to be similar in strategy. And what this means is that you really have, if you visualize it as some physical problem you're trying to solve, right? The way to solve the problem has to be innately similar and synonymous between all of these different tasks in your family of tasks. Another way to think of it is that you need a very similar skill set to be able to achieve mastery in all of these tasks. And another key thing is that with all of these tasks in this family, you can gain more experience by completing or learning how to learn more and more of these tasks. And once you have more experience, this experience is going to yield you a quicker and more efficient learning process whenever you take on a new challenge that's also part of this family of tasks. So for a real life example, you can think of maybe like a robot who's already learned how to, let's say, ski and jet ski and ride a motorcycle, but the robot wants to learn how to ride a bike, right? Since it already has all of this experience in learning how to ride the skis, the jet ski, and the motorcycle, tasks that are all really synonymous and require a similar skill set and knowledge to riding a bicycle. This robot is going to be able to learn how to ride the bicycle quicker and easier than if the robot had come into this task of learning how to ride the bicycle with no previous knowledge and no previous experience. Um, I guess another great example would be video games, right? If someone has mastered many of these video games in the past, then once they're given a new video game that's in a similar format to their old video games, they'll be able to use their previous experience to learn how to play and learn how to master this new video game with more ease than if they had gone into this challenge with knowing nothing at all and having no previous experience. And another point is that just for this lecture, we're going to stick with supervised learning problems just because we want to simplify what the base learner has to do in order to understand the processes behind the meta learner better. And one really easy way of creating a base learner, one really easy example, I guess, is having the base learner solve a simple supervised learning classification problem. So the example that we're going to use actually is similar to like a basic CNN that has to identify or classify an object that is in an image, right? And we're going to use this because it's a very simple and understandable example for the base learner, and we can build off of it very easily. So let's now dive into the process of training the actual meta learner itself. So we're going to start with our meta training set. So what the meta training set is comprised of, basically, you can think of the meta training set as being comprised of different subsets. And each of these, we can call them S train test 1, S train test 2, S train test 3. And through all of these subsets, even though they're subsets of the big overall meta training set, each one of these subsets is a complete data set in and of itself. So each of these subsets is going to include all of the features, all of the labels, and a training and testing portion. So it's just as if you were to pull any data set and use it to train a basic neural network. It's a complete data set in and of itself. And all of these subsets, they make up the meta training set. So if you can guess where we're going with this, basically each of these subsets is going to be used to train the base learner, while the meta learner is going to operate on the result of the base learner training on all of these subsets of data, or all of these subsets of data sets. So now let's say we're going to define all of these subsets, S1, S2, S3. Let's say that S1, you have to classify between cats and dogs, right? So you're given images with cats and with dogs in them, and labels saying, does this image have a cat? Does this image have a dog? Etc., etc. Let's make S2, I don't know, mice and rabbits, right? S3, birds and ladybugs. And all of these independent data sets, they're smaller, less extensive, but they contain a training set, a testing set, and labels for all of these images. So if we remember back to the purpose of our meta learner, the goal of the meta learner is to really sequentially train the base learner on all of these data sets. So S1, S2, S3, dot, dot, dot. So during the first step of training, the base learner is just going to do one forward pass through S1. And one thing that we have to keep in mind during this entire process is that when the base learner updates itself, it's going to be using the optimization function defined by the meta learner. So after one pass through S1, the base learner is going to calculate a loss, and then it's going to move on. It's going to move on, and then it's going to train itself one pass through S2. Calculate a loss here, and then it just repeats. And it's going to repeat this for S3, S4, however many subsets you have within your entire meta-learning set. So this entire process was basically one forward pass through the entire meta-training set M. After this one forward pass for the meta-learner, we have to calculate a meta-loss. So this can be calculated as the sum of all of the losses from the base learners. So remember in the forward pass we just did, right? We calculated losses for each of these training sets as the base learner was training on them. So S1, S2, S3, all of these have some loss that they were able to compute. And for our meta loss, we can just treat this as the sum of all of these independent losses from all of these subsets. Actually, we don't even need to call this a sum. Our meta loss can be calculated from all of the base learner losses. And we could treat this as the sum for simplicity of all of these losses. So moving on, the next thing we have to do is a back pass for the meta learner. So we have to calculate gradients with a backward pass through the base learner. So all of the training done by the base learner. And these gradients, you have to remember, these are gradients for the meta learner, and we can call them as such. We can call them meta gradients. And yeah, we're going to do a backward pass through the base learner training on all of these training sets, S3, S2, S1. And through this, we're going to be able to compute the gradients from the meta loss that we were able to gain through computing the losses from all the times the base learner is trained on the training subsets. And yeah, so with these aforementioned meta gradients, we're able to take these meta gradients and then feed them into the meta learner's model optimization function. So remember how we're thinking of the meta learner as just a meta neural network that's being trained in this higher level fashion over all of these base learners? Well, this meta learner also has its own optimization function for it to update its own weights and train itself. This optimizer for the meta learner, it's usually a predefined optimizer. So Atom, SGD, RMS prop. Yeah, I don't have enough space here. RMS prop. But I guess you could also get even more meta onto like a higher meta level and keep on making meta learners. But yeah, that would probably not work well and would not be a good idea. So anyways, this optimizer for the meta learner, this is going to update the meta learner model and thereby update the optimizer for the base learners. So if we remember again, this meta learner is training the optimization function for all of the base learners. So when the meta learner is updating itself, the optimizer that all of these base learners are using, that itself is going to be updated. Yeah, we could just note this as the meta optimizer just to not get confused. So yeah, this meta optimizer, it can be whatever you choose, and it's probably going to be a predefined optimization function. And once you use these meta gradients that are fed into the meta optimizer to update your meta learner model and thereby update the optimizer, we basically just completed an entire meta training step. So if we repeat through this process again, it would be another epic over the entire meta training set. And as we all know, you're probably going to want to run through this entire meta training set for many epics in order for you to achieve the best optimization function from the meta learner. And just as a quick recap, if we look back to all that we just did, we did a meta forward pass where the base learner was being trained on S1, S2, S3, and calculating losses, and this was one forward pass. Afterwards, you would take all of these losses, combine them into a meta loss, and then do a backward pass through all of all of these base learners once again, so back through S3, S2, S1, and compute gradients from your meta loss. And that entire process would constitute your meta backwards pass. And with these gradients that you've computed, you can feed these into your meta optimizer, your optimizer for your meta learner, and this will update the weights of the meta model itself. And through this, we're able to gradually refine the optimizer function that's defined by our meta learner model. And by repeating this process over and over, having our base learner keep on going through all of these subsets of the meta training set, all of these subsets S1, S2, S3, dot, 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 over and over again. And gradually using this more optimized optimizer function, we're able to really create this near ideal, hopefully, optimizer function defined from our meta learner. And the key takeaway here is that this optimizer that we're training using the meta learner, it's going to be able to, once again, quickly and efficiently solve any new tasks in the same family. And for this family, if we go back and look at what we were originally doing, right? We originally had our S1, which was classifying between cats and dogs, images of cats and dogs, S2 being mice and rabbits, and S3 being birds and ladybugs. If we posed a new question, right? Dogs or fish? We have this issue of being able to classify images if it's a dog, if it's a fish, or I don't know, if it's a bear and if it's a lion, right? And these are two new data sets that we want to be able to train really quickly. We can use this optimization function that our MetaLearner has just created in order to train these two new data sets, SX and SX plus 1, both with lesser training data possibly, and also just in general have them train faster. And actually, this plays into a concept called few-shot classification, which is basically this classification problem where you're given very limited examples and very limited training data and are asked to maybe classify between two novel objects, images of these two novel objects. And having such an optimization function that's able to train and new models really, really quickly and really, really well would be super beneficial to any few-shot classification problem. So there is also pseudocode in the lecture. It's pretty basic. You can take a look at that just to basically just review through this entire process. And I guess in conclusion, being able to learn how to learn quickly and efficiently, it's this immensely beneficial characteristic of being able to utilize past experiences to learn new things quicker. And I'm sure that the experience gained from meta learning is going to prove very beneficial in machine learning systems for years and years to come. Yeah, so thank you guys for listening. Thank you for watching. And wow, it was really, really tiring for my arm to write all of this, and trying to talk and write at the same time is also pretty challenging. But yeah, just tell me what you guys thought about it, feedback on if you like this lecture format better, or if, I don't know, you would prefer just having your traditional like whiteboard style lecture. But yeah, thanks for tuning in, and I hope to see you guys next time on our next virtual lecture in our virtual lecture series.